Hello, you're welcome to our chemistry class. In chemistry today, we shall be looking at the topic gas laws. Now, these laws basically have to deal with gases. Now, gases are known to have a physical state in which the molecules move freely throughout the entire space in which they are found. Examples of gases include oxygen gas, chlorine gas, hydrogen gas, etc. Now, gases are known to take the shape of a container in which they are found, and so because of that, we have certain characteristics of gases, such as the fact that number one, they do not have a fixed volume but expand to take any space available to them. Number two is that they have no fixed shape. Three, they can be compressed easily by applying pressure, and this is due to the large space between the molecules. So if you have a container like this, which is sealed, and here we have a pipe which lets in a gas, you'll find that the molecules of the gases, they will fill the entire space of this container and will be found moving about. And so because of this, you can compress them. When you compress them, they will take the space in which you have compressed them to. And then number four, they are transparent. One can see through a gas. Then they diffuse rapidly in all directions, and then when they are heated, they expand. Generally, we have about 7 gas laws. Number one, we have Boyle's law, we have Charle's law, we have Dalton's law of partial pressure, we have Graham's law of diffusion, Gay-Lussac's law, Avogadro's law. Then we have the ideal gas equation. Now, this ideal gas equation is not basically a law, but it is an equation that is relevant to gases. Okay, then we also have a general gas law, So in this particular first part of gas laws, we shall take the Boyle's law, Charles' law, and the general gas law. We move on to Boyle's law. Boyle's law states that the volume of a given mass of a gas is inversely proportional to the pressure, provided the temperature remains constant. Here we have that the volume is inversely proportional to the pressure, provided that the temperature is constant. Now, what does this mean? It means that the temperature does not change. The only thing that changes is either we increase the volume, and when we increase the volume, the pressure will reduce, and when we reduce the volume, the pressure will increase. So that's why we have an inverse equation, because when you increase this, this will reduce, and when you reduce the volume, the pressure will increase. And so because of that, when we remove this proportionality sign, we have that V equal to Kp, where K is a constant. So, alright, and then we have K equal to Vp. And when we consider a particular gas which has an initial volume and an initial pressure, and then the volume was increased to V2 and the pressure also decreases to P2, they are related with this equation, and then it is also equal to Tk, where we say that temperature and pressure are constant. The Boyle's law is graphically represented with an equation such as when we have a pressure here and we have volume here. So because they are inversely proportional, so as pressure reduces, it is noted that volume decreases. And if we plot the graph like this, where we have P and then an inverse of V, and if we plot the graph like this, such that we have pressure here and an inverse of V, we will take note that we will have a straight line graph such as this, because we have pressure and then we have inverse of the volume. Now let us solve questions under the Boyle's law. First question says, the volume of a given mass of a gas at 10 degrees Celsius and 600 millimeter mercury is 140 centimeter cubed. What will be the volume of the gas at 10 degrees Celsius if the pressure is 120 millimeter mercury? Alright, so in this question, we're told that we have a temperature of 10 degrees Celsius, and then we have a pressure of 600 millimeter mercury, and then we have a volume of 140 centimeter cubed. Now what will be the volume? So we have our V1 P1, and then what will be the volume if the pressure is increased to, so if the pressure is increased to 1200 millimeter mercury, still having a temperature of 10 degrees Celsius. Now we've noticed here that the temperature is constant. So because it is constant, we'll make use of this formula that has volume and pressure. So we have that V1 P1 equal to V2 P2, where this is our P2. Now the initial volume was 140 multiplied by the initial pressure, which is 600, equal to V2, which is unknown, multiplied by P2, which is 1200. And so making V2 the subject of this equation, we'll have 140 multiplied by 600 divided by 1200. And so we'll have 70. Hence, our V2 equal to 70 centimeter cubed. Let's take the next question. We have that a certain volume of a gas at 20 degrees Celsius has a pressure of 500 millimeter mercury. If at the same temperature, this pressure is decreased to 250 millimeter mercury, the gas now occupying a volume of 100 centimeter cube. Calculate the initial volume of the gas. Now in this question, we have that the temperature is the same, so we don't need to include the temperature here. But we're told that we have a pressure of 500 millimeter mercury initially, and then the pressure decreases. So we have an initial pressure, which is P1, and then we have a P2, which is 250 millimeter mercury. Then when the pressure decreased, we have that the volume changed as a result of the decrease in the pressure, and it changed to 100 centimeter cube. But we do not know the initial volume. So to calculate the initial volume, we have that V1 P1 equal to V2 P2. Our V1 here is unknown and P1 is 500, equal to V2, which is 100 multiplied by 250. And so we have V1 equal to 100 multiplied by 250 divided by 500. We have a volume, or an initial volume, of 50 centimeter cubed. Next, we shall look at Charle's law. Charle's law states that the volume of a given mass of a gas is directly proportional to the temperature, provided the pressure remains constant. Now, what does this mean? It means that the volume of a gas is directly proportional to the temperature. And what does this mean? It means that as you increase the temperature, the volume increases. So that's what the direct proportionality means, provided that the pressure remains constant. When we remove this proportionality sign, we have that V is equal to KT, where K is also a constant. Making K the subject of this formula, we have that K equal to V over T. Now, a situation where we have a gas which had an initial volume and an initial temperature, which both of them were increased to V2 T2, we'll take this particular formula, where both of them will be equal to the pressure and the constant. And then we have a graphical representation of our Charle's law like this, with this as being the temperature in degrees Celsius, and here we have our volume in cm cubed. Now we have the equation move in a straight line such that as volume is increasing, temperature is increasing. This is 0 degrees Celsius, and when we move to the back here, we have minus 273 degrees Celsius, because this is the absolute temperature. Now let's take note that at this minus 273 degrees Celsius, which is called the absolute zero temperature, it is the temperature at which the molecules of the gas no kinetic energy and practically no pressure. And let's also take note that when we are calculating questions that have to do with temperature in gas law, we work based on Kelvin. And we should take note that when we have a temperature in degrees Celsius, it needs to be changed to Kelvin. And how is that done? So our temperature in Kelvin equal to our temperature in degrees Celsius plus 273, and that will give us our temperature in Kelvin. And so let's solve questions under Charles' law. 20 cm cubed of a gas at 55 degrees Celsius exerts 160 mm mercury pressure. At the same pressure, calculate the volume if the temperature is doubled. Here we have that a gas has a volume of 20 centimeter cubed, and then it has a temperature of 55 degrees Celsius. It exerts a pressure of 160 millimeter mercury at the same pressure, meaning that the pressure is constant. All right, so at the same pressure, calculate the volume if the temperature is doubled. So if you have a double temperature, that's our T2, and that will be 55 multiplied by 2, that is 110 degrees Celsius. Now we have to find V2. First, we need to have our temperature in Kelvin. To get our T1, we'll add 273. When we add 273 to 55 degrees Celsius, we will have 328 Kelvin. Likewise, T2 will add 273, and that would give 383 Kelvin. Next, we'll bring in our formula, which is that V1 over T1 equal to V2 over T2. Since pressure is constant, don't feature here. V1, according to here, is 20 over our T2 is 328 equal to V2, which is unknown, over T2, which is 383. We'll cross multiply. V2 multiplies 328 and 20 multiplies 383. Hence, V2 equal to 20 multiplied by 383 divided by 328. And so we'll multiply this out. Our answer will be approximately 23.35 centimeter cube. Hence, that is the answer. Here's the next question. The volume of a given mass of a gas at 30 degrees Celsius is 600 centimeter cube. If the pressure remains constant, determine the temperature when the volume is 800 centimeter cubed. Now in this case, we have that the temperature of the gas equal to 30 degrees Celsius initially at a volume of 600 centimeter cubed. And then we have that the pressure is constant, so it is not needed here. We have to determine the temperature, which is T2, if the volume has increased to 800 centimeter cube. So first, we will change this temperature to Kelvin by adding 273. When we add 273, that would give 303 Kelvin. Then we'll bring in our formula, which is V1 over T1 equal to V2 over T2. Our initial volume is 600 and our initial temperature is 303. We have a volume of 800 over a T2, which is unknown. We will cross multiply, that is T2 multiply 600, that's 600 multiplied by T2 equal to 303 times 800, making T2 the subject of this. So we have 303 multiplied by 800 divided by 600. When we multiply this out, we would have 404 Kelvin as T2. Since we're giving our answer in degrees Celsius, we could change it into degrees Celsius. And so temperature in degrees Celsius equal to temperature in Kelvin minus 273. So that's 404 minus 273. And that leaves us with 131 degrees Celsius. So we could leave our answer here or here. Next, move on to the general gas equation. The general gas equation is gotten from the combination of Boyle's law and Charles' law. And it is simply gotten by saying that P1 V1 over T1 equal to P2 V2 over T2. And so with this This is the formula which will be used to solve questions that relates Boyle's law and Charles' law. Now we have that this equal to this and is also equal to constant, which the constant here is R. So let's take a question here. Question 1. A sample of a gas at 10 degrees Celsius and 150 millimeter mercury pressure occupies a volume of 500 cm cubed. What volume will it occupy at 50 degrees Celsius and 200 millimeter mercury? Now let's take our parameters. We have that the temperature of a gas initially was 10 degrees Celsius and it has an initial pressure of 150 millimeter mercury and then occupies a volume of 500 cm cubed. We have to find the new volume, that is V2, when the temperature has increased to 50 degrees Celsius and we have a pressure of 200 millimeter mercury. First, let's convert the temperature in degrees Celsius to Kelvin by adding 273. Here we have 283 Kelvin and over here plus 273 and that gives 323 Kelvin. Next, we'll substitute our values into this particular equation. Our P1 is 150 multiplied by V1, which is 500, divided by T1 is 283. That is equal to P2, which is P2, which is 200 multiplied by V2, which is what we are looking for, that is unknown, and T2, which is 323. We'll cross multiply, that is, this multiplies everything here. So we have 323 multiplied by 150 times 500 equal to, this multiplies this, so we have 283 multiplied by 200 times V2. Now with this, we'll make V2 the subject of this formula, where we have V2 equal to all this 323 multiplied by 150 times 500 divided by 283 multiplied by 200. When we multiply all this out, we'll have 428 as the final volume. Here is the next question, which says that a given mass of a gas has a volume of 750 centimeter cubed at 20 degrees Celsius and 120 millimeter mercury. Calculate the pressure at which it will have a volume of 700 centimeter cubed at 40 degrees Celsius. So we take down our parameters. We have that a gas has an initial volume of 750 centimeter cubed, and then at an initial temperature of 20 degrees Celsius and a pressure of 120 millimeter mercury initially. Now we have to calculate the new pressure, which is P2, when it has a volume of 700 centimeter cubed and a temperature of 40 degrees Celsius. Alright, so what we'll do first is to convert the degrees Celsius to Kelvin by adding 273. This will give 293 Kelvin and this will give 313 Kelvin. Next, we will substitute our values into this particular equation. P1 is 120 and then V1 is 750 over T1 is 293 equal to P2, which is unknown, multiplied by V2, which is 700, divided by T2, which is 313. We'll cross multiply, that is 313 multiplies all this. So we have 120 times 750 times 313 equal to, then this multiplies this. So we have P2 multiplied by 700 times 293. And so making P2 the subject, we have P2 equal to 120 times 750 multiplied by 313 divided by 700 multiplied by 293, and that gives 137.35 millimeter mercury as the final pressure. Now at certain times we are asked to make our calculations in standard temperature and pressure. Now, standard temperature and pressure refers to a standard, which is a point of reference for the purpose of calculations that have to do with gases. Now, the standard temperature is 273 Kelvin, which is the same thing as 0 degrees Celsius. And then the standard pressure is 760 millimeter mercury, or we use 1.01 times 10 to the power of 5 Newton per square meter, or we use 101,325 Pascal, or we use 1 atm, that is 1 atmosphere. Depending on the unit of the pressure we're given, it will determine which of these pressures we have to make use of. Now let us solve a question that relates this. Okay, an ideal gas at 30 degrees Celsius and 1.01 times 10 to the power of 5 Newton per square meter occupies a volume of 200 centimeter cubed. Calculate the volume at standard temperature and pressure. Alright, so here's the question where we have that an ideal gas has an initial temperature of 30 degrees Celsius, and then it has an initial pressure of 1.01 times 10 to the power of 5 Newton per square meter, and then occupies a volume, that is its initial volume, which is 200 centimeter cubed. We have to calculate its volume, that's V2, at standard temperature and pressure. So the standard temperature there means that we have to use the temperature which is standard. Now the standard temperature here is 273 Kelvin, and then the standard, so this is going to be T2, and then this is going to be P2. So the standard pressure that we'll make use of here, we will not use this, rather we will use this, because the pressure we're giving here is in Newton per square meter, and so that's why we use this. If we're given our initial pressure in Pascal, then we're going to make use of this standard pressure. If we're given our pressure in atmosphere, we'll use 1 atmosphere as the standard pressure, and so on. So the standard pressure we are going to use here is 1.01 times 10 to the power of 5 Newton per square meter. Next, we have this temperature in degrees Celsius, so we need to convert it into Kelvin, and that is done by adding 273, and that gives us 303 Kelvin. And so that's what we are going to use for the initial temperature. Next, we have our formula, which is P1 V1 over T2 equal to P2 V2 over T2. With this information, we substitute our values into this, and so we have our initial pressure, which is 1.01 times 10 to the power of 5 multiplied by the initial volume, which is 200, divided by, alright, this is T1, our initial temperature, which is 303, equal to standard pressure, which is P2, that is 1.01 times 10 to the power of 5 multiplied by the volume 2, which is unknown, so we have it as V2, over the T2, which is the final temperature, that is 273 Kelvin. And so what we'll do is that we'll make V2 the subject. We have V2, so that is all this multiply this, 1.01 times 10 to the power of 5 times 200 times 273, and then this will divide this, so we have 1.01 times 10 to the power of 5 times 303. So all this cancels all this, and so we are left with that. So when we make our calculations, we will end up with 180.20 cm cubed. Hence, that is our volume. And if you take a good look at this question, we will notice that the pressure is constant. Next, we move on to Graham's law of diffusion. Graham's law of diffusion states that the rate of diffusion of a gas is inversely proportional to the square root of its density. Mathematically, it means that the rate of diffusion is inversely proportional to the square root of its density. Now, if you consider the rate of two gases such that one gas has rate 1 and the other one has density 1, and then the second has a density of 2, and then we have 1 over the density of 2 for the second gas. Now, these two gases can be merged to arrive at a particular formula. Merging it will mean that we have this multiplies this, so we have R1 then square root of D1 is proportional to 1, and then we have R2 square root of D2 is proportional to 1. Since 1 and 1 are the same thing, we can equate the two. So we have R1 square root of D1 is proportional to R2 square root of D2. And so we arrive at a formula which is that R1 over R2 equal to D2 over square root of D2. Now this particular formula is very, very important. So this is our first formula that we'll be using in Graham's law of diffusion. Now to derive other formulas, we have that relative molecular mass of a gas is equal to 2 times its vapor density, which is this is the density. And so with this relative molecular mass could be substituted into this density. And so when it is substituted, if we have that, we have density of gas 1 and density of gas 2, then we have the relative molecular mass of gas 1 and gas 2. With that, we will have a formula that says that R1, R2 is equal to the square root of relative molecular mass of 2 over the relative molecular mass of 1. So we have a second formula here, which will be so relevant in solving Graham's law of diffusion. And next, so we have that the rate of diffusion is equal to volume of the gas over the time taken for it to diffuse across the opening. So with this, we could make use of our temperature. Now let us take note that at equal volumes, we'll have different time. And so at equal volume of the gases, where we have R1 V over T1 and then R2 equal to V over T2. At equal volume of the gases, we can substitute R1 with T1 and then R2 with T2. And so we'll have T2 over T1 is equal to square root of molecular mass of the second over the square root of molecular mass of the first. And so we have arrived at a third formula that we'll use to solve questions that relate to Graham's law of diffusion. Now first, diffusion is the movement of particles of a matter from a region of higher concentration to a region of a lower concentration through a medium. So there may be an opening of sorts to permit the particle to move. We have a question here which says that 400 cm cubed of a gas A diffuses through a porous partition in 5 seconds, and 200 cm cubed of a gas B diffuses in 20 seconds under the same conditions of temperature and pressure. A. Calculate the rate of diffusion of gases A and B. B. Which gas is denser? So let's first state our parameters. We have that we have to calculate the rate of diffusion of gas A and gas B. Here, rates equal to volume over time. The volume of gas A equal to 400 cm cubed, and it diffused through a porous partition in 5 seconds. Hence, its rate of diffusion is 80 centimeter cubed per second. And then we have gas B, which is of volume 200 centimeter cubed, and then it diffused through the partition in 20 seconds. And so we have 10 centimeter cubed per second as its rate of diffusion. Now with this, we've done the first part of the question. Then B, we're asked that which of the gases is denser. Now how do we know the one which is denser? This 80 centimeter cubed of this volume passed in 1 second, and for this 10 centimeter cubed passed in 1 second, meaning that this one passed faster than this. This one passed slower, meaning that this one is a bit denser. Denser has to do with being kind of heavier. So this is denser. So we have that gas B is denser. Next question says a gas X diffused through a porous partition at the rate of 2.5 centimeter cube per second. Under the same conditions, hydrogen diffuse at the rate of 10.0 centimeter cube per second. Calculate the relative molecular mass of the gas, that is the gas which we do not know, X. Now we have to find the relative molecular mass of the gas. And in the question, we're given the rate of diffusion of X as 2.5 centimeter cube per second. We're given the rate of diffusion of hydrogen, which is 10.0 centimeter cube per second. And next, what we need to get now is that we need the relative molecular mass of gas X. But can we find the relative molecular mass of hydrogen? And the answer is yes. So hydrogen has an atomic number of 1, and then it is 2, H2, so multiplied by 2, so we have 2 grams. Now that is the mass of hydrogen gas. There's a formula that relates rate of diffusion with molecular mass, and that is R rate of X over rate of hydrogen equal to square root of mass of hydrogen over the square root of mass of X. From here we have that the rate of diffusion of X is 2.5, so we have 2.5 over rate of diffusion of hydrogen is 10, so we have 10 equal to the molecular mass of hydrogen is 2. We have square root of 2 over the square root of our unknown. Okay, so with this we can cross multiply, that is we have m of x equal to 10 times root 2 over 2.5. This cancels this, and then this gives us 4 root 2. Square root of molecular mass of x equal to this. Now we can bring this 4 in here. It will become 4 times 4 times 2. So that is when the 4 comes in, becomes 4 times 4. And this is 4 times 4, 16. 16 times 2, that's 32, equal to mx. The roots cancels roots, so we are left with molecular mass of x equal to 32 grams. We have the next question here, which says 50 cm cube of ethane that effuses a small aperture in 10 seconds. What time is taken by 25 cm cube of carbon 4 oxide? We have to calculate the time taken. Now first, we have that the volume of ethane equal to 50 cm cubed, and it effuses at a time of 10 seconds. Now that is for ethane. Next, we have another gas, which is carbon 4 oxide, CO2, which has a volume of 25 cm cubed, and then we do not know the time it took it to effuse through the small aperture. Now for us to get this done, we can get our rates. So the rates for ethane to effuse equal to 50 over 10, and that is 5 centimeter cube per second. We can't calculate the rate of diffusion for CO2 yet because we do not know the time. So let's have that as X. Next, we calculate the relative molecular mass of ethane, which is C2H6. We have 2 of carbon, that is 2 times 12, plus hydrogen is 1 times 6. So when we add all this, we have 30 grams as the relative molecular mass of ethane. And then for CO2, carbon is 12, oxygen is 16 times 2. And so when we multiply all this out and add, we'll have 44 grams. Now there's a formula that relates the molecular mass with rates, and that is that rate of diffusion of ethane over rate of diffusion of CO2 equal to relative molecular mass of CO2 over square root of relative molecular mass of ethane. Rate of diffusion of ethane, we have it as 5. We do not know that of rCO2. Then the square root of relative molecular mass of CO2 is 44, and then relative molecular mass of ethane is 30. Now we take square root of 44 divided by square root of 30, that will give 1.211. And so when we multiply this with this, that's 1.211 equal to 5. And so RCO2 will be equal to 5 divided by 1.211. And so RCO2 will give us 4.1286 centimeter cubed per seconds. Next, we have that rate of diffusion of CO2 equals to its volume over time. We have our volume given as 25 over the time. And so we have our RCO2, which is 4.1286 equal to 25 over T. And so with this, we have T will be equal to 25 divided by 4.1286. We have approximately 6.06 seconds. So that is the time it will take. We have the next question here, which says that under the same conditions of temperature and pressure, hydrogen and oxygen gases diffuse through a porous partition. What are the relative rates of diffusion of hydrogen to oxygen gases? Now in this question, what we want to get is the ratio of the diffusion of hydrogen to oxygen. Now, first, we need to get the relative molecular mass of hydrogen and that of oxygen. Hydrogen, we have 1 multiplied by 2, and that's 2 grams. And then for oxygen, we have 16 times 2, and that's 32 grams. Those are the relative molecular mass. Next, we have that rate of diffusion for hydrogen gas over rate of diffusion for oxygen gas equal to the square root of molecular mass of oxygen over square root of molecular mass of hydrogen. The rate for hydrogen is unknown, okay? Then rate for oxygen is also unknown. But the relative molecular mass of oxygen is 32. And then for hydrogen, we have it as 2. Now let's take note that we can't just cut this out like that, except to rationalize. And so to solve this out, we will have, now we can say that square root of 32 is equal to square root of 16 times square root of 2. Now with that, we'll have these 2, we'll take out these 2. So we have R H2 equal to square root of 16 left over R oxygen over 1. Now with that, square root of 16 equal to 4 over 1. Meaning that the rate of diffusion for hydrogen equal to 4 and rate of diffusion of oxygen equal to 1. And what does this mean? It means that hydrogen diffuses faster than oxygen. That is, oxygen is denser than hydrogen. Move on to Dalton's law of partial pressure under gas laws. His law states that in a mixture of gases which do not react chemically together, a gas will exert a partial pressure, which is the pressure it will exert if it is kept alone in the vessel. And so if you have a gas here and a gas here, this gas will have its own pressure and this gas will have its own pressure. And the pressure that they have when they are put into a common container, both of them will exert their own pressure, which are partial pressure to each other. And so you have a total pressure, which will be pressure for A plus pressure for B. It may be more than 2 gases, so each of them have their individual pressure. This law is basically used when correcting pressures of gases collected over water, because when a gas is formed and it is collected over water, we should take note that the water itself has its own vapor, and so the gas which is collected over water is not the only pressure of the gas we will be having. We will have 2 pressures. So we have the total pressure will be pressure of the gas plus pressure of vapor. And so we'll have a total pressure which is the partial pressure of the gas which is collected plus the partial pressure of the vapor inside the container. Under Dalton's law of partial pressure. First question says 200 cm cube of nitrogen gas at a pressure of 500 mm mercury and 100 cm cube of carbon 4 oxide at a pressure of 50 mm mercury were introduced into a 150 cm cubed vessel. What is the total pressure in this new vessel? Now this, we have a container which contains nitrogen gas, and the volume of the gas is 200 cm cubed, meaning that to fill up the container. And then we have another gas which is CO2 inside the container, and it is 100 cm cubed. Now both of them were introduced into a vessel which is 150 cm cubed. Both of them are going to exert their own partial pressure. Now we know their partial pressure, we'll be able to get the total pressure. Now we're given the pressure of nitrogen gas here and the pressure of CO2 gas here. And so we'll have that the partial pressure for nitrogen will be equal to 200 over 150, because the 200 cm cube volume of the nitrogen gas had been put into this 150 cm cube times its initial pressure, which was 500 cm cubed, okay, which is 500 millimeter mercury over 1. And so when we multiply this out, we have 666.67 millimeter mercury. So that means that in this bigger place, it had 500 millimeter mercury of pressure, but when it was put into this smaller container, the pressure increased. Then we will find the partial pressure for carbon dioxide gas. We have 100 cm cubed of it over 150 cm cubed multiplied by its own initial pressure, which was 50 cm cubed. Now when we multiply this out, we have 33.33 millimeter mercury. Alright, so we have here that the pressure, which was 50 millimeter mercury here, has reduced. Why? Because it has been kept in a container which was larger than where it was before. And so the total pressure will be the partial pressure for CO2 plus the partial pressure for nitrogen gas. For CO2 we have 33.33, and for nitrogen gas we have 666.67. And when we add all this together, we have 700 millimeter mercury. That is the total pressure. Next question says that 50 cm cubed of a gas X and 30 cm cubed of a gas Y occupy a container with a capacity of 80 cm cubed. If the total pressure of the gas mixture is 760 millimeter mercury, calculate the partial pressure of gas X and Y respectively. Now we have that the volume of gas X equal to 50 cm cubed. We have a total volume of 80 cm cubed. And so to get the partial pressure of gas X, that will be 50 over 80 multiplied by the pressure exerted by the entire gas mixture, and that is 760. And so when we multiply this out, we'll have 475 millimeter mercury as the partial pressure of X. And then we have the volume of gas Y. We have it as 30 cm cubed. And so to get the partial pressure of gas Y, we have it as it is 30 over the total volume, which is 80, multiplied by the pressure of the gas mixture. And so we multiply this out, we'll have 285 millimeter mercury. Hence, this is the partial pressure of gas Y. Next question. Calculate the pressure of the dry gas collected over water at 10 degrees Celsius and 750 millimeter mercury, given that the vapor pressure of water at 10 degrees Celsius is 20 millimeter mercury. So this is quite easy. From this question, we have the pressure of the wet gas equal to partial pressure of the dry gas plus partial pressure of water vapor. We're told that the wet gas has a pressure of 750 equal to pressure of the dry gas plus pressure of vapor, which is 20. And so pressure of the dry gas will be equal to 750 minus 20. And so that will give 730 millimeter mercury as the pressure of the dry gas. Next question. 20 cm cubed of carbon 4 oxide gas at 20 degrees Celsius and 500 millimeter mercury was collected over water. If the vapor pressure of water at 20 degrees Celsius is 20 millimeter mercury, determine the volume of dry carbon 4 oxide gas at standard temperature and pressure. Now with this, we are given that the volume of the gas initially was 200 centimeter cubed and it was collected at a temperature of 20 degrees Celsius and 500 millimeter mercury was the pressure. Now we have 500 millimeter mercury as the pressure when it was collected over water, meaning that there is a pressure, meaning that is not just the pressure of the gas. It means that this pressure is that of the gas plus partial pressure of vapor. And so we are given that the pressure of vapor here is 20. To get the real pressure of the gas, we'll subtract 20 from 500 and that would give 480 millimeter mercury. Next, we have to determine the new volume of the dry gas at a standard temperature of 273 Kelvin and a standard pressure of 760 millimeter mercury. Alright, so the first is that we need to change this degrees Celsius into Kelvin, and that will be 20 plus 273, and that's 293 Kelvin. Next, we have our formula, which is V1 P1 over T1 equal to V2 P2 over T2. We are to find the value of V2. So if we make V2 the subject, we have V2 equal to V1 P1 T2 over T1 P2. Next, we will now substitute our values into this. V1 is 200, our P1 is 480, and our T2, which is this, is 273 divided by T1, which is 293, multiplied by our P2, which is 760. When we multiply this out, we will have 117.69 centimeter cubed as the new volume. We move on to ideal gas equation. Now these are gases that obey Boyle's law and Charle's law, and this equation is gotten as a result of combination of Boyle's law, Charle's law, and Avogadro's law. Boyle's law, which is that volume is inversely proportional to pressure, having that temperature and K are constants. And then we have Charle's law, which says that V is inversely proportional to the temperature, having that pressure, and we have a constant over here. And then we have Avogadro's law, which says that volume is inversely proportional to the number of moles, having temperature and pressure as constants. And so this equation is combined and we arrive at PV equal to nRT, where P is the pressure in Pascal and V is our volume in meter cubed. N is number of moles. R is a constant, which we'll get to know the constant in a minute. Then T is temperature in Kelvin. Now let's take note that when we have all these parameters with these units, we'll have our constant R to be equal to 8.314 Newton meter per mole per Kelvin. So this is the value of the constant, and there are times when the units of some of these parameters change, and when they change, for instance, when we have our volume in liter, and then in liter or in dm cubed, and then we have our pressure in atmosphere, and then we have our temperature still in Kelvin, R will change to to 0.821. But in this class, we shall be making use of R to be equal to 8.314. And then let's talk about the number of moles. We have that number of moles of a gas is equal to the mass of the gas over its molecular mass. And at times, we could have that density, which is equal to mass over volume, could be worked into this equation. And when it is worked in, we have that P multiplied by the mass equal to dRT. So here is another formula which is important in ideal gas equation. Let's take a first question on ideal gas equation. Determine the pressure exerted by 2 moles of a gas occupying a volume of 200 meter cubed at 50 degrees Celsius. Now first we state our parameters. We have to determine the pressure given that the number of moles is 2 and then occupying a volume of 200 meter cubed at a temperature of 50 degrees Celsius. And don't forget that we have a constant R which is 8.31 joule per Kelvin per mole. Our ideal gas equation, which is PV equal to nRT. Now from here we have to determine the value of P, so we can make P the subject. That is P equal to nRT over V. N is 2 multiplied by R, which and then the temperature we're given in degrees Celsius. And so we convert it into Kelvin by adding 273. And that will give 323 Kelvin. So we have 323 divided by our volume, which is 200. And so when we multiply this out, we'll have 26.84 Pascal as the pressure. 500 dm cubed of a gas at 30 degrees Celsius and 303,975 Pascal pressure is contained in a vessel. Calculate the number of moles of gas present in the vessel. Now we state our parameters. We have a volume which is 500 dm cubed, and then at a temperature of 30 degrees Celsius and a pressure of 303,975 Pascal. We have to calculate the number of moles present in the vessel. We have our R, a constant, which is 8.31 joule per Kelvin per mole. Now we have some parameters that do not have the units required to be used, which we require. First, we have this in dm cube, so we need to convert it into meter cubed. And to convert it, all we need to do is to divide. Now, since deci means divided by 10, and we have it in cube, so that will be divided by 1000. So that is 10 in 3 places. That's 10 raised by 3, and so that's 0.5 meter cubed. And then our temperature is in degrees Celsius. We need to convert that as well to Kelvin. So we have 30 plus 273, and that leaves us with 303 Kelvin. Next, we have our formula, which is PV equal to nRT. We have to find the value of N. N equal to PV over RT. Our pressure here is 303,975 multiplied by our volume, which is 0.5, divided by the rates, that is 8.31, multiplied by the temperature, which is 303. And when we multiply this out, we have our number of moles to be equal to 60.36 moles. So that is the number of moles of gas present in the vessel. Next question says, calculate the mass of carbon 4 oxide gas, which occupies 112 dm cubed at 27 degrees Celsius and 10 kilopascal pressure. So first, we have mass of carbon dioxide to be, now we have to find the mass of carbon dioxide, which is unknown, which occupies a volume of 11.2 dm cubed and at a temperature of 27 degrees Celsius and a pressure of 10 kilopascal. We have our R to be 8.31 joule per Kelvin per mole. Now in this question, we have to find the mass. but the mass is gotten from where we have number of moles equals to mass over molar mass. So first, let's get the number of moles. And when we get the number of moles, from there we'll get our mass. And so we have that PV equal to nRT. Now let's take note that we can have number of moles equal to mass over molar mass. We have to find the mass, and we can get the molar mass of this gas. Now this gas we're given is carbon dioxide. So we have mass of carbon dioxide. Carbon is 12, oxygen is 16 times 2. So when we add this, we have 44 grams. Now what we could do is that we have to find the mass, and we know the molecular mass. Why not substitute m over mm for n in this equation? Also, before we proceed, we need to have this in meter cubed. This dm cubed will be converted to meter cubed, and that will be done by dividing by 1000, and that would give 0.011 meter cubed. And then this temperature, which is 27 degrees Celsius, will become 300 Kelvin. That is, we'll add 273 to 27. So next we have that PV equal to nRT. Now we're going to substitute this n with m over mm. So our PV, our P over here is 10,000. That's kilo. Multiplied by our volume, which is 0.011. Then the number of moles is mass over the molar mass, which is 44, multiplied by R, which is 8.31, multiplied by our temperature, which is 300. This is 11.2, so we have 2 remaining here, and we have 2 remaining here. Now this will come over here. We have 10,000 multiplied by 0.0112 times 44 is equal to mass times 8.31 times 300. When we make m the subject, we have that m equal to 10,000 multiplied by 0.0112 times 44 over 8.31 times 300. We can multiply this straight, and so we have our mass to be 1.98 gram as the mass, and that is approximately 2 grams as the mass of the carbon dioxide gas. Next question says that 2 grams of a gas X occupies 5.6 dm cubed at 200 degrees Celsius and 20 kilopascal pressure. Calculate the molar mass of the gas X. Here we have a gas that has mass 2 grams, and it occupies a volume of 5.6 dm cubed at a temperature of 200 degrees Celsius and a pressure of 20 kilopascal. We have to find the molecular mass of this particular gas. We have our R to be 8.31 joule per Kelvin per mole. So first, what we should do is let's have our units right. This 5.6 dm cubed, we'll divide it by 1000 to have 0.0056 meter cubed. That is by dividing by 1000. Next, at 200 degrees Celsius is changed into Kelvin. We add 273, and that will give 473 Kelvin. And then this Pascal is now 20,000 Pascal. Our formula, which is PV equal to nRT. We have that n equal to mass over molar mass. And so we could replace this n with m over this. So we have PV equal to the mass over the molar mass times R times T. Now we have to find that is this m. To make the m the subject of this equation, we can bring the m over here, and that will become capital M equal to small m R over T over P and V. Here we have our molecular mass, and here is the mass of the gas. Now we shall substitute our values into this. So m equal to the mass of the gas, which is 2, multiplied by the rate multiplied by the constant R, that is 8.31, multiplied by the temperature, which is 473, divided by the pressure, that is 20,000 Pascal, multiplied by the volume, which is 0.0056. And so when we multiply this out, we'll have 70.19. Here is the molecular mass of gas X. Next, we move on to Gay-Lussac's law. Gay-Lussac's law states that when gases react, they do so in volumes which bear a simple ratio to one another and to the volumes of the products, if they are gases, provided temperature and pressure remains constant. Gay-Lussac's law applies to gases, and here is what it means. If you have a gas such as hydrogen reacting with oxygen gas to form water, we balance this equation by having 2 here and having 2 here. Now Gay-Lussac is saying that when gases react, they do so in volumes which are in ratio to one another. So we have 2 volumes of hydrogen here, and we have 1 volume of hydrogen here to produce 2 volumes of water. And so this is the ratio that he's talking about. Or if you have carbon monoxide which reacts with oxygen to form CO2, we balance this equation by having 2 over here and having 2 here. And so we have that 2 volumes of carbon monoxide reacted with 1 volume of oxygen to produce 2 volumes of carbon dioxide. So here is the simple ratio of the volumes. And then that will bring us to Avogadro's law. Avogadro's law applies basically to gases as well, and it is used to explain Gay-Lussac's law. And his law states that equal volumes of all gases at the same temperature and pressure contain the same number of molecules. In this, we could have a reaction that contains a solid, and so the volume of a solid is not accounted for. Make use of an equation where we have nitrogen gas reacting with hydrogen gas to form ammonia gas. We balance this equation by placing 3 here and by placing 2 here. Now from here we have that 1 volume of nitrogen gas reacted with 3 volumes of hydrogen gas to produce 2 volumes of ammonia gas. This question says, calculate the composition by volume of the resulting gas and the unused gas when each of the following mixtures are made to react. A. 70 cm cubed of hydrogen gas with 40 cm cubed of oxygen, and B. 10 cm cubed of hydrogen with 20 cm cubed of chlorine. Now let's take the first part. We have that hydrogen gas reacts with oxygen gas to form water molecule. First is to balance this equation. We place 2 here because we have 2 atoms of oxygen. Now we have 2 here, then we place 2 here to have 4 atoms of hydrogen and 4 atoms of hydrogen over here. According to Gay-Lussac's law, we have 2 volumes of hydrogen, 1 volume of oxygen, and 2 volumes of water. Now, they react in equal volumes. Now, in equal volumes, in this question, we're told that 70 cm cubed of hydrogen was made available and 40 cm cubed of oxygen was made available. So 70 cm cubed was made available for hydrogen, and then 40 cm cubed was made available for oxygen. This is the question. But the reacting mass is going to have the simplest ratio. Now if you consider 1 mole of hydrogen gas, 1 mole of hydrogen gas is 35 cm cubed, and then 1 mole of oxygen here is 40 cm cubed. Now what we are saying now is that we are going to make use of this smaller volume. This smaller volume here will react with this 35 cm cubed. We only need 35 cm cubed from the oxygen gas. since they are reacting in ratio to one another. And so if 35 cm cubed only was taken from oxygen, we will have 5 cm cubed of it left. And then we have 2 moles of hydrogen gas. And so 2 moles of hydrogen gas, since we have 1 mole to be 35, hence 2 moles is 70 cm cubed. And since we are making use of this smaller volume, we'll use the same volume to determine the volume of the water. And so we have 2 volumes of water, which is a gas, and that would give 70 cm cubed as well. So the volume of unused gas is this, which is unused oxygen, and here is the volume of the resulting gas, which is 70 cm cubed. Now the next one says hydrogen reacts with chlorine. Hydrogen gas reacts with chlorine gas to form hydrochloric acid. We balance this equation by placing a 2 in front here. According to Gay-Lussac's law, we have that 1 volume needed 1 volume of this to give us 2 volumes of HCl. Now from the question, we have that 10 cm cubed was available to react with 20 cm cubed of chlorine. Now with that in mind, we have that they react in simple ratio to one another. So 1 volume of hydrogen is 10, and then 1 volume of chlorine over here is 20. Now we're going to make use of this smaller 1 volume, meaning that out of this 20 cm cubed, only 10 cm cubed of it, since we are working with the smaller volume. Now if 10 cm cubed was used from 20 cm cubed, which was made available, we have 10 cm cubed unused of Cl2. And then to get our volume of the resulting gas, we are following the fact that we have 1 volume as we are using 10 cm cubed as the reacting volume. Hence, so if you have 2 volumes, we have 20 cm cubed of hydrogen chloride as the resulting gas. Next question says, calculate the volume of oxygen required to bond completely. A. 20 cm cubed of hydrogen. B. 30 cm cubed of carbon 2 oxide. Now in this question, the A part, we have hydrogen gas needing oxygen to bond to produce water vapor. We need to balance this equation by placing 2 here and placing 2 here. We're told that 20 cm cubed of hydrogen gas was provided as 20 cm cubed. Now there are some other things that we need to take note of. That we have 2 volumes of hydrogen gas and we have 1 volume of oxygen gas to produce 2 volumes of water molecule. And so what is the volume of oxygen required? If 2 volumes equal to 20 cm cubed, hence 1 volume will be 20 divided by 2, and that is 10 cm cubed. So volume of oxygen gas required is 10 cm cubed. Then the B part, we have carbon 2 oxide with oxygen to produce CO2. We balance the equation here because we have 2 of oxygen and we have 1 here, making 3. And so to balance it, we place a 2 here and we place a 2 here. So we have 2 of oxygen making 4, and then 2 times 2, that's 4 oxygen atoms. We are provided with 30 cm cubed of carbon monoxide, 30 cm cubed, and we have to find the volume of oxygen gas required. Now, since 2 volume equal to 30 cm cubed, hence 1 volume will be 30 divided by 2, and that is 15 cm cubed. And so since we have just 1 volume of oxygen here, so we have that volume of oxygen gas equal to 15 cm cubed. Next question says 50 cm cubed of carbon 2 oxide and 30 cm cubed of oxygen were allowed to react. Calculate the composition of the resulting gas. All measurements being made at the same temperature and pressure. Now in this question, we have carbon monoxide plus oxygen gas to form carbon dioxide. Now we balance this equation by placing 2 here and then 2 over here. Now all these are gases. Now we're told that 50 cm cubed of carbon 2 oxide and 30 cm cubed of oxygen reacted. We have to calculate the composition of the resulting gas. Now here we have 2 volumes of CO, we have 1 volume of oxygen, and we have 2 volumes of CO2. And the resulting gas is this, so we have to find the volume of the resulting gas. Now we consider that 1 mole of oxygen here is 30 cm cubed. Or we have that 1 volume of oxygen here is 30 cm cubed. And 1 volume of CO over here is 25 cm cubed. And so we use this 25 cm cubed because it is a smaller volume. Then if we use 25 cm cubed from the 30 cm cubed of oxygen, we have 30 minus 25. So we have 5 cm cubed unused. Then for the resulting gas, we have here that 2 volumes. Now 1 volume is 25 cm cubed. So 2 volumes will be 2 times 25, and that is 50 cm cubed. Our resulting gas is 50 cm cubed. Here's the next question, which says, if 40 cm cubed of hydrogen were exploded with 50 cm cubed of air, assuming air contains 80% nitrogen, 20% oxygen, calculate the composition of the resulting gas. All measurements being made at room temperature and pressure. Now from here, we have hydrogen gas, which is containing 40 cm cubed, and then with air, and air is a composition of gases such as nitrogen and oxygen. Now we're told that the nitrogen in this air is 80% of the entire volume, which is 50, and for oxygen is made up of 20% of the entire volume, which is 50. And so when we calculate this out, we'll have 40 cm cubed as the volume of nitrogen, and we have 10 cm cubed as the volume of oxygen. Now let's calculate the composition of the resulting gas. Now when you have hydrogen being burnt in air, it is only the oxygen that will react, because the nitrogen will not react with the hydrogen. And so we have hydrogen plus oxygen gas to produce water, that's the vapor. We balance this equation because we have 1 atom here and we have 2 atoms here. So if we place 2 here and we place 2 here, the equation is balanced. Now if we have 2 volumes of hydrogen here and we have 1 volume of oxygen to give us 2 volumes of water molecule. And from what we have here, we are told that 40 cm cubed of hydrogen was made available, and 10 cm cubed for oxygen was made available. Now with this, 1 volume is 10 cm cubed, and then 1 volume of hydrogen here is 20 cm cubed, because 2 volumes is 40, hence 1 volume is 20. Now we won't use the volume for hydrogen because it is bigger. Rather, we'll use the 1 volume of the oxygen. Hence, the volume of water molecule we are going to have here will be 2 times 10, which is the smaller volume, and that is 20 cm cubed. So from here, we will have that the volume of the resulting gas, we have hydrogen gas as a resulting gas, then we have unused gas, which is hydrogen unused, and out of the 40 cm cubed, we use just 20 cm cubed. So we have 40 minus 20, and that is 20 cm cubed of unused gas. And don't let us forget that we have this nitrogen gas, which is also a resulting gas. So we have a nitrogen gas of 40 cm cubed.